Hi class, this is chapter 8.3. We are looking at mole to mole conversions with balanced equations. So if we look at a balanced equation, that's going to be in terms of a recipe. It gives us our vital information in order to figure out what we need, how much we need to produce, how much we need to put in, and so forth. So if we look at this reaction here, we have in the reactants, we have 3 moles of hydrogen plus 1 mole of nitrogen, and this produces 2 moles of ammonia. We can also use the word molecules. There's a lot of things that will come up. We can use moles, we can use mass, we can use molecules. Molecules we don't tend to use as much. Moles tends to be the key term that we use, but while you're learning, molecules will come up later, definitely. But if you look at either one, we can say there's 3 molecules in this reaction, 3 molecules of hydrogen, 1 molecule of nitrogen, 2 molecules of ammonia, 3 moles of hydrogen, 1 mole of nitrogen, and 2 moles of ammonia. So moles tends to be the easier one to understand, and that's the main one, but we will use molecules coming up. Not in this section, but it'll come up. So what if we have 3 moles of nitrogen? So we would, just like with the eggs, we had more eggs, so we wanted to see how much more we could produce. This is the same thing. If we have 3 moles of nitrogen, how much, and more than enough hydrogen, which we would call excess. We have an excess amount of hydrogen. We don't need to worry about that. How much more nitrogen ammonia can we make? So we need to have a step, a plan to do this. So we take the moles of nitrogen and we want the moles of ammonia. But in between here, we need something that's going to allow that to happen, and that is this ratio. We can take the ratio from this compound reaction. So we need moles of nitrogen, so we can place 1 mole of nitrogen on the bottom, and we have 2 moles of ammonia on top. We're taking everything straight from this balanced reaction. Why is moles on the bottom? Because in stoichiometry, the unit you want to get rid of is on the bottom, because what we do is when we write 3 moles, technically what this is if you draw a line here and put a 1, it's in the numerator position. You can cross things out from a numerator and a denominator position. So with the 3 moles of nitrogen, we can use the 1 mole of nitrogen, cross that out, leaving us with the moles of ammonia, which is what we want, and our final answer in this being 6 moles of ammonia. This is a very simple problem and how to set it up, and even the most difficult problems, this is how you're going to set them up. Don't lose track of it by getting confused on a lot of things. The setup rarely changes except for when we have to convert from the numerator and the denominator, which will come up later, but right now it's simple. Don't get confused about how we set this up. This is as simple as it can get, no matter how, and you can bring this into a more complicated problem. Okay, so let's look at equation here. We have 2 moles of iron, 3 moles of sulfur, and 1 mole of iron 3 sulfide. So when you see this, this is how you can read it. Moles, 2 moles, 3 moles, and 1 mole. Now from this information though, we can take a lot out of it. We can get our mole to mole factor, which can be used as a conversion. So from this, we can look at the relationship of iron and sulfur. We have 2 moles of iron to 3 moles of S, 3 moles of S to 2 moles of iron. Why are these are the same. So why are they like this? It's because it's a ratio. We can use them any way we want to, depending on what we need to convert units from. Now we have iron and iron 3 sulfide. We have 2 moles for 1 mole of iron 3 sulfide and 1 mole to 2 moles of iron. Again, we can flip these any way we need to in order to solve our problem, as long as the units cancel. And then we have sulfur and iron 3 sulfide, and we also have a ratio of those. So this is important. This balanced chemical equation isn't just a balanced equation. We can pull out a lot of information from it, and that's what we're going to start doing in order to do calculations. So let's look at this equation here. We have 3 moles of hydrogen, 1 mole of nitrogen, 2 moles of ammonia. And you can see we can pull out the same information. We can do a mole to mole factor from hydrogen and nitrogen, the reactants, and we have a mole to mole of ammonia to hydrogen. So it's asking us for a mole, which is the correct mole to mole fraction between hydrogen and nitrogen. Well, we know we have 3 moles of hydrogen. So the first thing we need to do is look for 3 moles of hydrogen, and we have it here. So this one doesn't matter because it's not correct. We only have 1 mole of nitrogen, And this one doesn't have, we don't even have 2 moles of hydrogen. So B is going to be correct. And on the bottom one, I mean on the nitrogen to hydrogen one, we still have 3 moles. So best thing is to look for 3 moles. We have 3 moles here. We have a 3, but that's for nitrogen. So this is going to match, and we can confirm it with the 2 moles of ammonia. So we can see, we can pull out the correct answers for these. These are our ratios that we can use in order to convert. How many moles of iron 3 oxide can form from 6 moles of oxygen? So we can take this equation, and now we again can set it up in a very simple form to determine how many moles we need. So this is a mole to mole factor. This is a conversion we're using based on the balanced equation. So we start out with 6 moles of oxygen. The rule is that the units that you want to get rid of are on the bottom. So that's why we have it in 2 different setups. So you can see what you need, and which way you need it is how you set it up. So we have that. We have 3 moles of oxygen on the bottom, 2 moles of iron 3 oxide. These cancel out. Our final answer is 4 moles of iron 3 oxide. Okay, so how many moles of iron are needed for the reaction of 12 moles of oxygen? We're going to do the same thing here. We're going to set this up with 12 moles of oxygen, and we're going to look at a ratio. It's asking for moles of iron. So we want this ratio, and we want this ratio. So the ratio between these is 4 moles of iron for 3 moles of oxygen, and how we set this up, which goes on the bottom, which goes on top, is depending on how we want to, what the answer is. So we're given 12 moles. We have moles of iron. We need a mole to mole factor, which I've already explained. So you have to look at your quantities. This is taking a lot of steps in slowing this down from what I'm showing you. But if this is something that looks complicated, then follow these steps. Pull everything out, so then you can figure out what the next step is. So the next step is to write a plan. So how are you going to get from one to the other? A stepping stone. So we start with moles of oxygen. We need that mole to mole factor that we can pull out from here to get to moles of iron. And if we're correct, the moles of oxygen to cancel out, leaving us with moles of iron. So here we have our conversion. This is our equality, and that means 3 moles of oxygen is equal to 4 moles of iron based on this balanced equation. And now we can pull out our ratios from that, and you can set it up whichever way it needs to be in order to cancel out. So we have our 12 moles of oxygen. We set up with 3 moles of oxygen on the bottom because we want to cancel this out, leaving us 4 moles of iron. Do all the calculations, and we end up with 16 moles of iron. And now you need to start paying attention to sig figs. I will get more into that as we go. These do not count because these are exact numbers that are going with this. They're not measured numbers. And that's it.